So this will be an example of how we compute a bearing-bearing intersect longhand with a calculator. Now, why is this important? For one, when you do it with any kind of software, you need to understand what it's doing and be able to detect problems. That's the difference between being a technician and a professional, is you can not only detect problems that otherwise go unnoticed, but you can also troubleshoot them with your knowledge. Now, we're not going to do a whole lot in the real world in our jobs with a calculator like this, but this is the logic and the theory behind what we do. Now, I've got 3 slides we'll work through. It's the same slide, but we'll work through what we're going to be given and what we've got. Now, the other reason to know how to do this longhand and understand the math behind it is this is probably as simple or the simplest question that you might see on your PS exam. This is like the foundation building blocks of surveying. So what are we going to be given? This is what we're given. All right, and we'll start with the basics. We are given everything in this red box. We have coordinates on 11 and 12. And so we can work that out and determine that the azimuth is 650118. And the distance is 177.046 between 11 and 12. I've given you coordinates on 11. I say I gave you coordinates on 12 too, but you've got all that you need with this azimuth and distance to compute coordinates on 12. We're trying to determine coordinates on number 13 over here across the parking lot. So we have horizontal angle turned from 11 backsiding 12, and we have the interior angle at 12 backsiding 13 to 11, or an angle left, or however you wanted to derive it, but that angle is 94/1702. So what's in red is what is given. So what do we know right off the bat? Well, we know that n minus 2 is 1 times 180 is 180, so the sum of the interior angles of any triangle is 180 degrees. So you subtract 94/1702, the angle at 12, and 39/2243, the angle at 11, from 180, and you get your first new computed value, 46/20/15. Now, this is just straight up law of sines that tells us that the opposite side length from the sine of the angle that it is projected from, that same relationship carries through to the rest of the triangle. So we know that 177.046 is our length, and we'll just say of 1112. And we know that 46/20/15 is 46.3375 degrees. Please be sure to convert degrees, minutes, and seconds to decimal degrees. The sine of that angle is 0.7243. So when you do the math, our little magic formula right here is our law of sines constant is 244.735. Now, as I've said, everything in surveying can be checked a roundabout way. So what I've done here is we take our law of sines constant, 244.735. That's going to be the same as, follow me here, 11 to 13. That's our long side, the southernmost side, divided by the sine of the angle opposite it, which is 94/1702, which is 94.2839 degrees. Do the math, and we get that 11 to 13 is 244.051. So yes, we're getting there, and that's feet. Also, we know that 12 to 13, that was 11 to 13, so 12 to 13 divided by the sine of the angle opposite of it, which is 39/22/43, which is 39.3786. we do the math, and that comes out to 155.27 feet. So we have derived our distances, our lengths of these triangles from the law of sines. And we also, let's just go ahead and do this. Knowing that this azimuth is 650118, add 392243, and you get this azimuth, 1042351. Take the back azimuth from 12 to 11, add 180 to 265, and you get, or add it to the sum 65, and you get 245. Take 94 off of that, and you get a resulting azimuth of 150.4406. So now we've got everything in green computed for us, and this is just simple. This is like the first step. Is we're going to turn the angles and get the azimuths. We're going to do the law of sines and get our distances. So let's go to a clean sheet here. We pretty easily now we know how to compute latitudes and departures. So we're going to take our azimuth and distance and get the latitudes and departures for each of them. So remember, latitude is the cosine of the azimuth times the distance. So we're going to start and say, okay, the azimuth is 104.2351. The distance is 244.05. This is going from 11 to 13. The latitude is cosine of that azimuth times 244.05 gives us negative 60.683. The departure is the sine of the azimuth times the distance. Take the sine of 104.2351. Always convert all these to decimal degrees. That gives us a departure of 236.386. Now let's stop right here for a minute and look at what we're doing. We're going from here, and north is up the page. We're going from 11 to 12. So we know we're going down in north or y value, and we're going up in x or east value. So that is confirmed right here with our computed latitude and departure of 11 to 13. We're going down 60 and over 236. That's kind of a visual check. Now, if you come up here to 12, we're going to look at the same process. Cosine of the azimuth times 155.27 gives us a latitude of negative 135.45. Let's say 3. I carried it to 4 decimal places out of habit. I often do that. And then the departure is the same. It is the sine of the azimuth times 155.27. The distance of the leg gives us a departure of a positive 75.904. So that makes sense. We're going down in value in a y or northern direction, and we're increasing in the x or easting. So that's confirmed right here. We're almost there. So here's another clean redo. We take our given coordinates of 11, simply add our latitude to our north and our departure to our east, and this is what we come up with. The coordinates to 3 decimal places of number 13. Just take this northing of 11, add the latitude departure. This is the result. Here's the check. Come up here to the coordinates of 12, add your latitude and departure from it, and bingo, you get the same value. Would not have surprised me if we would have been 1/1000th of a foot off. That's why we carry preliminary calculations like this, coordinate geometry calculations, to 3 decimal places minimum, because if we're off 1/1000th, that's just barely a few hairs. It's not a lot to worry about. But this is how you would come up with the coordinates, which we have now solved for. And we're going to be, yippee yippee. Here's our coordinates. This is the answer to the question. So if you're given the coordinates of 2 points and the angles from those 2 points to a third point, you can solve for the coordinates very precisely using this simple format. That is bearing intersects in 10 minutes or less. I'm Mark Chastain. Thank you.